Okay, so here is our first real static equilibrium topic for the course. We're going to do equilibrium of a particle in 2 dimensions, and it is sections 3.1 to 3.3 in the book. So here is the main concept for equilibrium of a particle. When you add up all the forces, they have to add up to 0. So in the homework up to now, and the problems we've been doing up until now, we've been getting the resultants, adding up all the forces, and they've certainly not been 0. The reason for that is we're not drawing in all the forces on a body. And so to be able to draw all the forces on the body, you have to be able to draw the free body diagram. Okay, so now for a comment. I feel drawing the free body diagram, or FBD, so for now on I'll just say FBD, which means free body diagram, is one of the most important concepts in this class. So therefore, you must draw an FBD for every problem. This is the most common source of mistakes in problems, drawing an incorrect FBD. And I have my own how to do it that's different from the book. And this concept will be more important when we get to equilibrium of a rigid body. And by the way, drawing FBDs involves drawing. And this is why we've moved away from Mastering Engineering. You cannot draw things on Mastering Engineering, the online homework. And it actually, not being able to draw it, teaches students to not value free body diagrams, or they try to have a free body diagram application on Mastering Engineering, and it's horrible. And so students do not know how to draw free body diagrams when they solely use Mastering Engineering. So it was so bad, we decided to abandon Mastering Engineering. On the other hand, Learning Catalytics, as you saw, does have modules where you can actually draw on your phone and it'll show up. So that's important. So this is what I feel is foolproof procedure for drawing a correct free body diagram. The steps are: draw a closed shape around what you're interested in, or a closed loop. Okay, the shape, and by shape I mean loop. Redraw the item inside your closed loop. If you don't mind ruining your original drawing, you can just draw on the drawing like in the book, but if you want to resell the book, you don't want to draw in the book. And then draw all the forces inside your closed shape or loop, and then draw in any forces that are cut by your closed shape. We will practice this a lot when we get to chapter 5, but let me do a quick example for you. So here's a problem we've done earlier, but let's say the new problem is draw the free body diagram. So the first step is to draw a closed loop or shape around what we're interested in. So we're interested in this little hook. So I'm going to draw a shape around it. So there we go. Okay, so the next step is to draw everything that's inside that shape. So I look at it, I've got that, here's the hook, and I've got this rope that's in the loop, and I've got that rope in the loop. Okay, that's step 1. Okay, step 2, draw any forces that are in the loop. And so all those forces that I've cut through are actually outside of the loop. But let's say there's the weight of the hook. Let's say it has a certain weight. Here's the center of gravity, and there's the weight. That would be inside of the hook. So the next step, it says, is to draw everything that red line is cut through. So it cut through that, which was 250 newtons. It cut through this, which was 400 newtons. It cut through this, which was 300 newtons. And it cut through the ground. And what we're going to learn later in chapter 5 is when you cut through something like that, you cut through a Y force, an X force, and we will learn this later. There's a concept called moment, and we're cutting through this moment. But anyway, this is the correct free body diagram for this, and it's using these steps that I used earlier. Draw a closed loop, draw the item that's in the loop, draw all forces that are inside of the loop, and draw all forces that the loop cut through. So now that you have the picture, the free body diagram, we will use the main equation for equilibrium of particle, which means all the force vectors have to add up to 0. The vector has an x and y components, so the sum of the force vector equals 0 means there's two scalar equations. It means all the x components have to add up to 0, and all the y components have to add up to 0. For equilibrium of a particle in 2D. Okay, so it's particle in 2D. You have only two equations. So here's a question. If you have two equations, how many unknowns can you solve for? And the answer is 2. So here is how to solve 2D particle equilibrium problems. Step 1, draw the free body diagram. This is non-negotiable. Step 2, set up the two equations, sum fx equals 0 and sum fy equals 0. And there will always be only two unknowns. There might be a little trick, but when it's all said and done, it'll boil down to two unknowns. So in this class, whenever we have an equilibrium problem, there will always be just the right amount of unknowns. This way, you can determine the solution. Okay, you can determine the solution, and the phrase we use for that is statically determinate, which means you can determine the solution using statics. In future courses, you'll have more unknowns than static equations, and you'll have to use some other type of equation to solve for the extra unknowns. But that is outside the scope of this class, so just a reminder, there will always be just the right amount of unknowns